Well, she said, I'm Boyd, Southeastern Biomedical. And wow, that is loud, isn't it? I'll try not to talk too loud here. I tell you, over the years, I've been doing this for 38 years now as a biomed. And during that time, I've learned a lot of things. And when I was in biomed school, my instructor said, okay, you're going to know about 1/1000th of what you need to know to do your job. And I thought, man, I've just spent 2 years in school. What do you mean? He was exactly right. So what we're going to talk about today is using the right tools, and this has come about from questions that I have got on routine basis. Now, just a little bit about it, why these questions come to me. I'm one of the owners, Southeastern Biomedical, and part of our company, one of the divisions, we have a metrology division, calibration. So a lot of this is really where that comes from, that we're going to be talking about here today. Now, obviously, I kind of like this guy's innovation here a little bit. And one other thing, guys, speak up if you've got something. I'd like to make this interactive, if you will, here for us. But needless to say, this guy, he's got some innovation. I don't know if OSHA drove by that this would exactly fly with them. And we may not do something quite as outlandish as this, but how many of you ever done that to start a screw before? I see heads nodding. Go ahead, admit it. I've turned that drill around backwards and just kind of tapped it a few times like that before I went ahead and started drilling it in. Isn't that what that was made for? Hey, works for me. Well, not exactly here. All right, so today what we're going to be talking about here, we're going to be talking about different standards used in testing. We're going to be talking about the specifications of our device under test. We've got to take into consideration. We've gone to look at test devices and look at their specifications. We're going to look at tolerance. We're going to look at all kinds of things. We're going to be talking some numbers here today. All right. Who can tell me the difference between precision and accuracy? How many of y'all want a precise test device, whatever you're using? You want something that's precise? Would you rather have something that's accurate? Would you like to have something that's both? Okay, let's go for both on this one here. All right, a lot of people get these terms confused. When we're talking about precision, we're talking about reproducibility. So in this example right here, you know, I've got all my little arrows grouped up right in the center. Man, that guy is precise. But what if they were all grouped up, say, right here? Would that be precise? Absolutely, because we're looking at something we can reproduce. Now, we wouldn't be very accurate with what we're doing, but we would be precise on it. So when we're talking about precision, we're talking about reproducibility. And when we're talking about accuracy, okay, we're talking about a tolerance. How much can we vary from something here? Now, one of the first things here, let's talk about how to read specifications. All right, when you look, okay, when you're buying test devices, what criteria? Budget. It could be that, well, it's yellow, it's blue, it's green. That's the ones I like. Okay. I find that a lot of people do not really look at the specifications of what they're buying and what they're using. And when you get into it, it can be very confusing, because it would be nice if everybody said, okay, this is so many percent, that's my tolerance. Good, we're there to go. It don't happen that way. All right, so the first thing that you'll see a lot of times here is percent of full scale or range. Now, let's take something and let's say, we'll say a voltmeter. And it says that it'll go to 100 volts. Now, I use 100 a lot because I can do the math with that a little easier here. So let's say it's 5% of full scale range. So if I'm measuring 100 volts, how much can I be off? 5. 5 plus, 5 negative, right? Okay, that's not too bad. All right, so if I'm measuring 10 volts and I have a 5% of full range, how much will I be off? 5. So all of a sudden, this thing that went, okay, great, I'm with 5% accuracy, I cut it down and I'm measuring something at 10 volts, I am 5% of full range. So that 0 to 100, I'm 5% of this. So if I'm trying to measure something at 10 volts, now what's my percentage of accuracy that I've got? 50%. Is that very accurate? Nope. You see this a lot, especially when you're doing flow, gas, and pressure measurements. So be very careful when you're looking at this stuff as, okay, I always try to stay away from test devices that say full scale or full range on them because of this, and people do not realize that. Percent of reading. So if I said 5% of reading, okay, if I'm at 100, all right, I'm allowed, 95 to 105. Now, if I do 5% of 10, I'm like, what, 1 each way on that? So it makes a big, big difference. Now, here's the one that I get a lot of, and I see people get confused. That little, and I should have put a percent in there maybe, but you can say, do you see that plus or minus? And I ask people, well, what does that mean? Well, that means if it said plus or minus 1, they go, oh, that's plus or minus 1%, right? What that is a plus or minus of your least significant digit. So if you're looking at this, and this multimeter, for example, says, 12.50, and we had a 1 there, plus minus 1, what would be our tolerance in this? It would be 0.01. So that last digit, it could be, 51, 0.51, or 0.49. So that is not a percentage typically like that. And that goes, have to look, how many digits do I go out? Now, maybe on this multimeter here, I'm measuring 1,000 volts. Now, that plus or minus, if it's a 1, I'm going from 999 to 1001, because now I put 4 digits after I don't have room for that decimal point. So that 1, that least significant digit, is that 1 holder there. So when you're looking at these, look and see, okay, exactly what are they telling me? What are my percentages? Things of that nature. All right, now let's get into some of the good stuff here. One of the questions I get, people will call in and go, I need a 10 kilogram weight. First thing I ask is, what class? You hear how quiet it is in here right now? That's what I get on the phone almost every time. How many people know the classifications of weights out there? Okay. F to 0, which kind of doesn't make sense, and F is now a class 7, and you can go into ultra class things of this nature. Okay, let's just skip over and get into some of the good stuff here. All right, so weight classifications. The lower the number, the more accurate that is going to be. A tighter tolerance on it. Now, here's what's funny. I ask people over there wanting, say, this 10 kilogram weight. And I say, what class do you want? Well, what class you got? I want the most accurate thing there is. Take a guess, if I done a class 0, 10 kilogram weight, what that would run. Somebody, how much you think that would cost you? Somebody throw a number out. double that. Somewhere around $1,900 for that 10 kilogram weight that you're going to use to take up and go to measure and put on that standing scale that has the little thing you roll across right here and to measure. Do we need that? No, we don't need that. Here's the other thing. You know, when go to calibrate that 10 gram class 0 weight, your calibration cost went from $35 to about $400. So we don't want to overkill things. But you can see here, like on that 10K weight, you know, okay, the class 7, which is used to be the old class F in there. You know, that's what you're going to find, you know, that 10 kilogram weight that's cast iron that you put your number on and everything like that. Now, let me say this. You get, we've actually seen this. People will have very accurate weights. All right, they want to keep up with, they need an ID number, right? What's the first thing they do? I see you smiling. You know what's going to happen here. They take their little etcher and they start etching a number on it. What just happened to that weight? It got lighter. You changed it, guys. Or you'll see they'll put a metal tag on it. All right, one that you've got 2.2 grams, that metal tag, you can write on it with a Sharpie. You can, it ain't going to matter with that. But you get down into, instead of, you know, where you've got what, 0.013 gram tolerance. All right, when you start etching that thing or you put your little metal ID tag on there, guys, you just ruined your $1,900 weight on that, because it ain't no good at that point for that stuff here. So you can see as we go out here what the differences are in this. So how do you determine what class you need? Okay, you can look in the manual. Just look in the manual of your scale. Unfortunately, they are not very good at saying, okay, you need a class 4, class 5, class 7. This is something that you're going to have to try to determine yourself. All right, we're talking about accuracy here. Now, in the calibration metrology world, when we come on site to do your calibrations, what we are looking at and what we have to do, we have to have something that is 4 times more accurate that I'm testing with than whatever I'm testing. So if you've got, easy number here, if you've got 4% tolerance on this device, I have to have 1% or better. We'll talk about this a little bit more as we go on here in a minute. Okay, now for you guys, you really don't have to go to that extreme. Typically what I see, if you can at least get 2 times, 2 to 3 greater accuracy than what you're measuring, you're going to be okay. All right, I pulled here from a manual. Here is a baby scale. Maybe I should have took the name out of it here. So my Detecto baby scale, this is all it has. It doesn't give me anything for testing, doesn't tell me what I need, anything like that. But it does give me a hint in here in that very top line there where it says capacity. So on that 10 kilogram right here, it has 10 kilograms times 0.005 kilogram. All right, what's that telling me? It's telling me what that least significant digit is. So what I'm looking at here, it can measure up to 10 kilograms, and it's going to do it in 0.005 is 5 grams. Let's move that decimal point over 3 spots here. So we can, it measures in 5 grams. Now, do we want something that is equal to 5 grams? No, let's go back here a second. So if we were going to pick a 10 kilogram class, what would we pick? Somebody take a guess. You could. 4 would be very accurate. What about this one here? Because we are a little better than 2 times more accurate. Remember, that thing will measure in 5-gram increments. So we are at 2 and 2.2 here. So, okay, so that kind of works for us. We could do that. You could move up to a class 4 and that'd be very good. Nothing wrong with that. All right, let's talk about this here and kind of put it into real life a little bit. So let's say I've got a weight that 100 grams. And let's say that thing is 5% tolerance. All right, so this weight I've got, it's 100 grams and it's 5, ooh, that's bright. Okay, and let's say it's 5% low, just barely falls within. So that 100-gram weight now weighs what? 95 grams. Everybody with me on that? Okay, let's say our scale has a 5% tolerance to it as well, and it goes to 100 grams. I put my weight on that scale, and it measures 105 grams. Now, the scale has to be within 5%, right? I know one thing about my weight. It's 5 grams lighter than it should be. Still falls in tolerance, right? So when I read and I look at my scale and it's reading 105 grams, what's the actual reading? 110. Wait, everything is measured in tolerance. That's because we used a 1-to-1. So now this scale that we're using, maybe it's measuring, up in your neonatal nursery. We're measuring urine output. We're weighing diapers. That's extremely important. We want to know how much that stuff weighs. So we want to make sure we're accurate. That's why you can never do a 1-to-1. Now, if we get to a 2-to-1, we can still stay within that range of that 5%. Now, we could be at the very hairy edge of one or the other of it, but we know that we're still going to stay within that. So that's why, when you're looking at stuff, whatever it is, look at those specifications. And I know what happens. I ran a biomed shop for years. How did I buy my test equipment usually? I've got $1,000 for budget. This one's $999. It wins. I mean, let's be real. But is that always the best choice? No. Okay. So like I say, I get this a lot. So weights, classification. Let's talk here a little bit about handling them. We do a lot of weights, obviously, here. I see these things, the way they're handled, the way they come in, and it just appalls me at sometimes. Okay, have you ever seen people use the little tweezers and stuff to pick up weights or put on the gloves? The whole reason we're doing that is to keep lint and oils and things like that. Because it would amaze you when you get into some of these little weights. We'll check it one year, the next year it's heavier. Why is it heavier? It's picked up dirt. It's picked up the oils and stuff from our fingers, and stuff has stuck to it. Now, you can't just take, when you're dealing with these very accurate weights, you can't just get the Windex out and take your Brillo pad and scrub it off and okay, it's nice and shiny. You can kind of use denatured alcohol or something like that very lightly. But again, think about what you're taking off while you're trying to clean this thing. I see people when they've got a scale and they put their weight on it. They take, and what do? They set the weight on there. All right, now we're going to talk about here, let's talk about one other thing for this. We really should measure a scale in several different places. We call it the quadrant method. quad means 4, but there's 5 places we're going to check this thing. We're going to put it in the center and each corner. Why? Scales have different load cells in different areas. Things may happen to it where it doesn't measure correctly. How many times do they put that baby right in the center of that scale? You know, Junior's sitting there and he's rolling around and he's active and stuff, so we need to test the whole area of it. All right, but I see people, they'll put the weight on there and they'll go to the left corner. They slide it over. They slide it to the right one, slide it to this one, slide it to that one. What happens every time you slide metal against metal? It's kind of like a file. Now, are we going to see that? No. It happens a couple of times. Is it going to affect it? No. You do it enough, it actually starts to affect the readings of it. And if you've got a super accurate weight, because you've got some of these up in your lab, these weight sets, they're $3,000, $4,000, $5,000 for one. There's a reason that they bought that. We can't just slide them around and handle them. However, we pick them up with the tweezers. Now, do not use metal tweezers. If you notice, they're always plastic. So don't grab, you know, your little tongs or whatever. That's because, again, metal. We try to stay away from that. All right, guys, secure these things. It's amazing to me how many times that we get weights in, weight sets, and they're not in any, they show up in a box. And in that box are 5 or 6 weights, and they're just in the box. Nothing sitting there, and they've been clinking around. Now, we know UPS, FedEx handles everything with kid gloves here now, so nothing would ever get tossed 20 feet away, drop kicked over to the next line or anything. Guys, what happens every time those bump together? It's just like dropping one. You know, you drop it, okay, your big 10 kilogram weight, you know, that you've got, you probably don't need to get that rechecked. Just hope you missed your toe when you done it. But these little things, yes, those have to be recalibrated if you drop it. So what happens when they're sitting there rolling around like this, you know, for 3 days, getting from one side of the country to the other? You know, and we'll call people up and go, hey, sorry. And by the way, before we ship this back, you're going to have to buy something, because I'm not going to ship it back the way you shipped it to me. So we want to make sure of that. Don't put these things near magnetic sources. If you think about, you know, how many of you, I used to keep a pacemaker magnet on my bench. Does everybody know what that is? Yeah, big round magnet. You know, they put it over a pacemaker, it stops it for a while here. I always kind of wanted to play with one just to watch it myself. But what did I do? I hung my screwdrivers on that. Why did I hang them on that? Because when I went to use that screwdriver, it was magnetized now. So it would hold my screw and I could do what I needed to with it and move it around. All right, if we have a weight that becomes magnetized, what happens when we set it on this metal plate of our scale? It does, and you may not feel it. You may not know it. It ain't where you're going to pick it up and the scale is going to come with it. But it's either going to have one or two things. I ain't sure which the effect is. It's either going to try to suck it down or it's going to try to pull that load cell up. What happens? You know, you think about gravity. Scales. Let's say I go to the coast and I calibrate a very precision or accurate scale. And then we ship that thing back to Denver, Colorado. It's changed. Why? The gravitational pull, every one of us, we weigh less when we go to the mountaintop in Denver, Colorado than we do at the beach because of the gravitational pull. Same thing with weights. Now, I will say that, quick story, our head metrologist. Now, this guy, he just amazes me. I walked in one day and anybody ever watch Big Bang Theory? Okay, yeah, I'm one of those. I like it. And you know how Sheldon has his board and he's doing all this? Well, I walk in, our guy Mike, he's sitting there and he's doing this big long calculation. And it's like, Mike, what in the world are you doing? He said, well, I've got to calculate the buoyancy of this weight. You know, of course, me, I'm sitting there going, it's metal, it don't float. And he looks at it and goes, well, the battleship floats. Okay, you got me there. But he was actually calculating how much buoyancy of this weight within air so he could get the accurate uncertainty that he needed for these calibration procedures. It's like, wow. Needless to say, very, very precise here. Okay, we talked a little bit about this. Okay, let the thing warm up. Yep, we're good. Everybody knows, you know, always zero it. I tell people zero it 2 times, because a lot of times you'll hit 0 and you'll watch it and you'll see it change by 0.1 or something like that. Hit it again. We talked about, okay, quadrant method. You should do it, your measurement on it, a couple of times. Run that thing around the scale a couple of different times while you're at it to see if your readings stay the same. Again, we want that precision part of it. We want to be able to reproduce this each time. And also, if you can, test the full range of it. You know, if it goes to 10 kilograms and you only got a 5 kilogram weight, are you really doing a good performance check or PM on it? No, because you don't know what's happening above that top 50% here in things. So you want to do the whole thing. Okay. Here's the other one I get. People call in and they'll go, I need a thermometer. All right. What kind? Help me out a little bit here. Many different types of thermometers out there that we deal with. Now, some of the most common ones are our thermocouples that we have. All right, so let's talk a little bit about this. And we're talking about the right thing to use. How many of you use a multimeter, your little bead probe, and plug it in there? And you may have a little adapter that goes with it. I've used those things 1,000,000 times in my career. You know, I've got a blanket warmer, blood warmer, something. That's how I always did it, the way I was taught. But let's look here a second. So I've got my trusty Fluke 87V. Look at my tolerance. Okay, I have to look at 2 things here. All right, you know, we're measuring on a voltage scale, millivolt is really what it is. But I've got to put in my probe or my little adapter there. So with my voltage, I've got 0.05%. That's accurate. I'm good with that. But when I plug in my little adapter that I'm going to plug my bead probe into, so instead of I've got a Fluke 77, let's say, don't have the hole for that. What happens? All of a sudden, my accuracy goes out the window. How many people actually, you might look, okay, I looked at my multimeter, I know how accurate it is. How many people actually look for the probe or the adapter? When we've got different test devices we're bringing in, we have to bring in every single piece of it. Kind of go back to, think about this when you're out doing PMs. How many of you have done a PM, you know, safety test on an endo cart? Nobody? Okay, all right. You know, on that endo cart, what is it? You've got your light source, you've got an ESU, it may be sitting on there, you got your video screen, you got this, that things, you've got your water pump, all this, you've got all of these devices. Now, when we test that, when we safety test it, what does NFPA 99 say we have to do? We have to test it as one entire system. Now, I see a lot of people get this wrong. They'll unplug each piece and test it. You can't do that. You test each individual device for your resistance, but you have to test that cart as one system. It's plugged into that one power strip down in the bottom. It's run all the way across that OR room. Same thing happens here. We've got to look and see every piece that's within that and take that into consideration here. All right, the other thing that we need to take into consideration, this Fluke 52, great accuracy, yeah. good product. You know, see them all the time. All right, so we've got that. You know, it's, like I say, it's an accurate device here. And I just lost my train of thought of where I was going. Oh, all right, that device, it will test to 900 degrees Celsius. That's hot. How many of you ever looked to see what your probe limitation is? Your probe may only go to 200 degrees Celsius, 50 degrees Celsius. So you plug in your probe, you go to whatever it is, you test it and go, wow, that's broke. It ain't heating up hot enough. You've got to look at your probe, because your probe is now your limiting factor of your thermometer that's in there. A lot of people do not look at it. Okay, so you need to take into consideration what you're doing here. All right, I've got a chart. If y'all want it, stop by and see me at my booth. I will give me your email. I'll send it to you. You'll see it here in a second. So we got thermocouples. We got RTDs. All right, anybody ever heard of a 4-wire resistance test? Okay, I'm gonna teach you something here. Does your multimeter measure resistance? Nope. Ah, gotcha. You went too soon. A multimeter cannot measure resistance. A multimeter calculates resistance. Ah, I know, it's a trick question here. That'd be a good one to put on the certification exam, maybe. Okay, because what we do, we put in a current, we measure a voltage coming back, you know, voltage over current equals resistance, Ohm's law. So your multimeter, if you ever want to get people on that, does not actually measure resistance, it calculates it. Well, an RTD is very accurate, and it works similar to what we call a 4-wire resistance, where I will take something and I'll put a current in on 2 leads, and I have 2 separate leads to measure it coming back, so that current that I'm injecting into that is not taken into effect or causing a problem. It's just a more accurate way of doing things that we have to do sometimes. Yes, yes, good example. Okay, so that's for something that's very, you need, they're not cheap, and that's for something that you need something that's very extremely accurate, but it's going to be expensive to you. All right, we've got thermistors. Okay, it's kind of like the RTD. The resistance changes as temp does. You see the ranges here. Okay, we ain't gonna get into all that. Here's kind of a generalized chart. So you need to think about, okay, what am I measuring? Okay, if I need to measure the lab fridge and it goes to a negative, whatever, let's, 100 degrees. Okay, we know that that one's not going to work. Okay, that'll work, okay. Now let's see how fast does it need to get there. Just be aware when you're doing temperature measurements, there's all kinds of different things. Now, when COVID hit, you could not find one of the little infrared things. Lowe's sold out of them, and everybody is trying to do it. Why didn't they work? All right. Anybody ever heard of the term emissivity? All right. Boy, all kinds of new stuff here. Emissivity basically is how well does something reflect energy. So something that is very shiny reflects energy better than something that is very dull. All right, so we have basically 0 to 1 in this scale. All right. Human skin has an emissivity of 90.98. I think that's kind of unique, 98 degrees, 0.98. The ones you buy at Lowe's hardware are 0.95. Throws everything off. So if you're measuring, let's say, sterilizer, I've seen people do it. Those things, they're measuring the heat bands going around the autoclave. Very shiny, isn't it? You need something that would have an emissivity that is lower than even that 0.95. And that's just some numbers that kind of go along. But you can see, a polished aluminum, 0.05. Well, if it's the anodized, just the regular old dull looking aluminum, 0.77. That's why you can't use those things for just anything. Just be aware of that when if you're trying to do infrared on stuff. All right, let's talk about incubator testing here a little bit. This is one, again, I find that even some of this, a lot of people do not have an idea of what all we need to measure. All right, if I asked you in here, how many of you know what the sound level limit is for an incubator? You're close. The international standard, according to IEC 60601-something, is 60 decibels. Now, the Academy of Pediatrics says 45. Why is this so important to us? Why do we measure it? How many of you as a kid like to have a big old box and go walking inside of it and start talking? You know, your voice changed. It got louder. Inside that incubator, that's a little amplifier. What have we got in there? We've got motors running. What happens when motors start to go out? They start to get louder. So I see this a lot of times where people, okay, they stick their multimeter in there and maybe a humidity meter or something like that, a hygrometer, but they really don't measure all of the things that need to be done. Again, let's talk about the accuracy of things. You know, I stick my 87V in there, which has an accuracy of 2.2, and what this of 2.2 degrees C. The Draeger, I just looked in the manual, Draeger isolate says, okay, you cannot have a temperature change more than 0.8 degrees C. All right, I know already I cannot accurately, if I've already got a span of 2.2 on this. The other thing is to every time think about this as well. What happens every time you open and close that incubator? The temperature. I'll even go one further. The environment changes on that. I will tell you, when we go on site to do calibrations, you know, we have to warm up our equipment. It has to be warmed up for about 30 minutes before we can start doing calibration. So that's why you know, whoever comes does it, you'll see them, they'll sit on, they'll turn it on first thing and do all of this stuff. All right. Trying to think how to put this gently. We've had people that have tried to put us in the tractor shed or different things like that. Let's say we were mobile doing this, and I had somewhere and I'm taking it outside the building and I keep opening a van, a truck or something like that. What happens every time that door opens? The environment changes. Then I have to wait 30 minutes, if I do it correctly, before I ever start that calibration. And that's the same thing we're doing here. So, and guys, and the reason I use Fluke Light is because I'm familiar with their stuff. I don't sell it here. I do in other parts, but this is not a sales pitch. I just know it, okay? So you need to look at something when you're doing incubator testing that you can do everything, set it in there, do it, let it go do its thing, and measure it without having to keep opening and closing it. All right, let's see how my time's running. Okay, all right. Billy meters. Here is something that I see a lot as well. Are people measuring Billy meters, especially the LEDs, with old, or Billy lights with old Billy meters? Okay, if you look, most of the older Billy meters that are out there, you know, we still see them made by Omeda. There's Natus, a lot of them. Those things typically run 450 to 470 nanometers. Now, here's the other thing. What we're measuring here is radiance. Guys, I have seen people try to use a regular light meter and they go, well, as long as it stays the same, I'm good year to year. No, you cannot do that. Radiance is measuring more of, or this in this case, a very narrow spectrum of things. Whereas when you're using a light meter, it's basically measuring what the human eye can pick up. So the newer, which most everybody has gone to, are LEDs. Look what range that runs in, or what they typically are, 480 nanometers in that spectrum. Look at your Billy meter when you get back. Look at your Billy light. So if we're measuring something at most of the old ones go 450 to 470, I'm not getting an accurate reading now on my nice little new LED Billy lights that I'm using. Okay. So let's talk about luminance and illuminance a second here. Luminance is the amount of light that's emitted by something. Illuminance is the amount of light that is hitting something. There's a difference in it. Okay, go into your radiology area. How many of you know the standard for measuring your radiology reading screens? Yes, there is a standard, and those things should be measured at least annually on it. So what we're doing, since we're measuring what is radiated, what it is emitting, we have to measure that in luminance, or candela per meter squared is the unit. If we're trying to use something that measures in lux, which is my illuminance, no, you're using the wrong device. You are not going to get an accurate number. So mammography, that is something, those reading screens have to be brighter than a typical X-ray. Look at what they're trying to find. They're trying to find that most minute, and you'll see them. You know, you walk up and they've got, you know, sitting in front of the screen, and they've got the magnifying glass and they're looking over it. So that is a higher standard that has to be met for mammography reading over just the one they're using to see, did I break my arm on things here. Okay, illuminance, different meter, typically so many lux. Okay, and that's just, you know, like light sources, things like that. All right, I'm gonna go back to calibration here for just a second. I've went on site and was talking to someone and said, okay, your Billy meter has to come back for calibration. And they were like, well, no, I'm sorry, our previous company done them here, why can't you? It's because I have a $20,000 light bulb, and I've got, it is strictly, I mean, controlled current, I've got distances. And I said, just curious, how did the other person do that? They said, well, he's got a calibrated Billy meter. He holds one right here, he holds the other right here, and if it reads the same, it's calibrated. I said, do your lights run at that 400 and some nanometer spectrum? Huh? This guy was coming in, and he was doing that, and even what reading he was getting was only about 2% of range. Feel free to question your calibration people when they come in, what you're doing. Not all are created equal. But anyhow, you know, we're looking, you know, all of these, you've got to have the correct device. You know, you're measuring radiance, luminance, and illuminance. You've got to have the correct device, or you're going to have the wrong reading on it. All right, let's talk about calibration standards here a little bit. All right, typically what you get, anybody in here from a manufacturer? Okay, typically what you're going to get on your calibration, you're going to get a certificate, right? Now, I'm going to tell you another story here. It's kind of, I was at a trade show, and I asked a guy, you know, I said, just curious, who does your calibrations? He said, we ain't done them in 5 years. And I gave him a look. And he said, you know, that's the same look you gave me 2 years ago when I told you this. He said, Joint Commission never asked for it. Until they ask for it, I'm not going to do it. Don't go to that hospital. I wish I knew what one it was just to tell on them, just about. But what you're getting, you're not just looking for a cert. This guy, he didn't even care about that. But typically you're going to get as found, as left, which is what we call the standard calibration. Now, why do we want to know the as found on this? Anybody here have D and V? Okay. What does D and V say? That if you find a piece of test equipment out of tolerance, what do you have to do? Yep, and you have to at least do a sampling, a percentage or something. So you need to go back to the last known good one, probably a year ago. All right, so that's why any of them will let you know it was in tolerance, out of tolerance. Okay, if it was out as left, how did we leave it? Well, it worked. Okay, in tolerance. Some places want data with theirs. They want to see the data points. Typically, because people don't want to pay for it. They're doing it, but like anything else, it just takes longer for the technician to sit there and do it, and everybody knows you can charge a little bit more for it, but you don't need it. You're good. The last one is ISO 17025. And we get this a lot. You know, it's like the weights. You know, it's, oh, well, give me the most accurate one you got. Well, I want the best calibration you got. Well, ISO 17025 is a certain calibration that can be done that's going to give you data, then it's going to give you uncertainties of your test device and all the things that you don't need to do, that you don't need to worry about. And that's something that you're going to pay probably 3 times the amount for. It doesn't matter, quite honestly. Now, when we get into manufacturing, you know, I'm sure the UPS plane that crashed, when they went back, and there's a lot of metrology in there, I'm sure a lot of that stuff in their devices are tested to 17025. You don't need to worry about that. Now, I will say this, and pretty much everybody out there is, you want to make sure that your cow company does at least have that certification and that capability. And there's a difference between people who go, well, I'm 17025 compliant. Okay, when were you audited on that? Well, never. We get audited 4 times a year with our ISO certification. I tell people, I've got Joint Commission 4 times a year that come through. They actually sit down, they witness, they watch the technicians, they go through it. Makes them nervous as all get out when they've got a guy just standing behind him, just watching him run his procedures. And this procedure may take 20 minutes or an hour or something. One guy, darn it, he was so nervous he blew about 5 fuses within the first 5 minutes, and the inspector said, all right, take a break, just calm down. I know you know what you're doing here. But you want to make sure that because they have demonstrated that they have a quality program, and it looks at a whole lot more than just the actual act of it here. But that is something you want to make sure of. There's only one company that doesn't have that, that's running around. So most everybody does. Okay, the last things here, you know, consider your operating environment, where you're using stuff. We kind of all know this. Inputs can change outputs of stuff. You know, if you've got dirty power, you can have bad results on things, stuff like that. We talked about, you know, elevation, humidity, different things of that nature, and that is it.